Good morning everyone, welcome to my YouTube channel, and for this video let's talk about the subsequent problem to the Sudoku problem. So for this problem we have to actually come up with our own Sudoku solver. So we will look at two approaches for doing this problem. Here is the problem statement, and as usual I want you guys to try this on your own before we look at our solution together. Like the traditional approach for solving this kind of problem, so this problem is similar to that n queens problem. I don't know if you have encountered that problem, but they are exactly the same. And so the first time I tried this I used backtrack on my own, but I actually encountered a really nice way of solving this problem, I think from MIT course like a few years ago, and just want to share that with you. So in the description I will have a link to the professor's paper. So backtracking, as you know, we try every single number, and then if that doesn't work we backtrack, we go to our previous step, and then we undo our the changes that we made. And basically we are doing so this, for using backtracking on this, the time complexity would be enormous. It is very huge, and especially when you are working on, say, a very difficult Sudoku. Typically that means we don't have that many numbers shown in the our Sudoku. Then in that case the number of times we have to do backtrack can get really big. So let's first look at the traditional way of doing this kind of problem. So as you know, here is the code. I put this backtrack variable here so that when you run this, we can see how many times our code actually had to do the backtrack. And you can see that, so basically we will be iterating from this guy 0, 0 all the way to 8, 8, and then we move to the right, and then see that this guy is empty. So we try all the valid numbers, say from 1 to 9, and we notice that, so in this case the first number would be what? 4. We try number 4 into here, and then so that would be here. So for E in range of 1 through 10, so that will be 1 through 9, and then in this case we check if it is valid or not. So the first valid number in this case would be what? I think this one would be 2, or actually this one would be 1. So we put 1 here, and then we check, and then we run this recursive function again. That's the main idea for this kind of problem. But as you can see, this one is very slow, right? Even if you use this code for the Leetcode problem, it will still pass. I think a few years ago when I used code very similar to this, I was able to pass, but it was rather slow. And I think right now it might be even slower because Leetcode typically has it adds more new test case. So I don't know how this would slow down, but this code works, so there is no problem with this. However, there is a way to speed this up. So there is a way to optimize this code, and let's look at that second approach. Oh, also I just want to emphasize that we have this inner block. So we have this 3 by 3 block here. So we can call this 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's say if you are working on this block like this guy, and you want to know which block, remember we have to check this inner block to see if the numbers are valid or not. In this case, if you are say here, then you would have to, then we'll be working on this block, right? And then the way I do that is you use this guy, so sector top x, sector top y. So you'll be doing 3 times I, this division by 3. So basically in this case, let's say if you try 7, 6, so I is 7, so we'll get 3 times 2, that will be 6, and then we would get 3 times 2, so that will get us 6. So it will be 6, 6 right here. And then notice that we can do this. So for that we add sec top x and then sec top x plus 3. So we'll be iterating from here to here, and the same thing from here to here. That will be given by sec top y, sec top y plus 3. So that's for this code, and there's really not much to do. And then we have our like this, we have if I is equal to -1, then we exit, we return true, and then we do exit. I think that's pretty much it. So let's look at the second approach. This is our second approach, but this is optimized. How so the previous approach is how computers tries to solve this problem, right? But then for us human, we do it slightly different way, right? If we look at this, we can cross out. So we know that this one has to be 1 because when this is 1, when 1 is here, that this guy, for this row we cannot have 1 here. When 1 is here, this row cannot have 1 here. Obviously you can also not have 1 in this column, 1 in this column, but for now we only care about this inner block. And then we look at this 1 again, and we notice that this column cannot have 1. So you look at this and we see that, well, all these blocks are invalid for 1, and then this one is already taken, this is already 6, so that means that one has to be 1. And then so that's the way of we reduce the number of times we have to run our backtrack function. Let's look at this one. So let's look at like really specific example what I mean by this. So here so instead of trying every possible combination, we can determine which numbers are valid at every block, like this guy, this one. So for each inner block, we would say like this 3 by 3. That's what I mean by inner block. We see which numbers are available. In this case, well, what? 2, 3, 4, 5, 7, and 9. So those are the available numbers. And then for each inner block, we determine which numbers are valid in the row and column. And if we are left with like single number, then we can place the number into the block. So what do I mean by this? This means we will get, say, row set, column set, and then we will be using our Python difference function between sets, and then we can just get rid of these like redundant numbers. And then when we are left with one number, then that number goes into like here. So let's look at a really specific example to see what I mean by this. So if you look at this 0, 0, that's the first empty block in our Sudoku, and we notice that, so we will be trying from 1 through 9, and we see that 5 is the first available number, and that is valid because, well, you may say, well, how about 2? 2 comes before 5, but then notice that 2 is here, so we cannot use 2. 5 is the first valid number, and then so we set that equal to 5, and then we look at all the other empty block in our inner block, this first block. So we see this guy, and this guy. So those 3 are empty, and then we will store like the coordinate, x coordinate, y coordinate, and then the missing number in this inner entire block. So in that case, we have 2, 8, and 9. So this is what I mean by this. And then you will be appending this to some list here, like that I will show you in the later code. And we notice that, and then the next step will be, we'll be looking at this one first, 0, 1. We check the rows of row of 0, 1. There will be this row, and then those numbers are what? 1, 3, 5, 6, 7. And notice that our this set and then this set, they don't have any numbers in common, so there's nothing we can do. We look at the columns of 0, 1. We notice that that's this guy, and then we have 3, 5, 6, 7, and 9, and we have 9 as a common number. So this one, for this one, 9 disappears, so we are left with 2 and 8. However, the length of this set is not equal to 1, so we cannot do anything. We cannot put any we cannot make an educated guess in here, so we move on to the next one. There will be this guy. Now for this guy, same thing. We look at the row and then the column. We notice that the row of 2, 0, it is 1, 4, 6, 7, and 8, and 8, the number 8 is the the common number, so 8 disappears from here, so we are left with 2 and 9. However, columns of 2 and 0, we have 3, 4, 5, 7, and 8, and there is no redundant number, right? We are looking at this set, and then we are looking at this set. They don't share any common number, so the length of this is still 2, and we move on to the next one. We have 1, 4, 6, 7, and 8, and we notice that 8 is the common number, so 8 disappears, and we have 2 and 9. Columns of 2, 2, we have this guy, And notice that this guy and this guy, they have 9 as a common number, so we are left with 2. Thus the length of this set is equal to 1, so we set that equal to 2, and we do the same thing for like all these blocks, right? The remaining blocks. And this is a lot faster than, you know, trying all numbers without making like this educated guess. So that's 2 here, and here is the code for that problem. So one thing that so this part is, you know, we are basically trying to find all the missing numbers in our inner block. And then here, this is the part where we do like this part. And then this part, we are finding so we are using this difference function, and then we find the first row v, which is equal to which is initialized as a set, and then we add all the numbers in here, and then we use the difference function, and then we try to, you know, get rid of this redundant number. We do the same thing in the column, and we try to get rid of redundant number if it is possible. And then if the set left has a length 1, then we pop that, and then we set that equal to, you know, the value here. So in this case, that's what I just did here, this part. And then we add this to this imply 1 array. So why should we do this? Well, we'll be running this, we will be making this educated guess, and then if somewhere down the road, when our, you know, this Sudoku solver cannot solve this, then we have to undo all the changes that we made, right? If you look at the code here, right, so this is basically here. So when we return, then when we backtrack, right, this is the backtrack part, we have to undo the changes that we made. Before we make the change to some number, then we have to make that change back to the like 0. So we have to do the same thing. However, in this case, it's slightly more complicated because we have to make we have to undo the changes for all this, like all the changes that we made under this imply 1. So that's why we have to store all these changes that we made in our imply 1 array. That's the key part. And then if you look at this one, I just pulled this out from some, like, you know, Sudoku app, and this is one of the really hardest problem. And if you use the naive approach, like the traditional backtrack approach, the number of times we have to do the backtrack is nearly 2 millions. But if we use the second approach, then we do roughly 60,000. So that's about 33 times faster than our naive backtracking approach. I really find this approach really powerful. And let's look at the Leetcode problem. Here is the code that is optimized for Sudoku problem, and it's exactly the same code that you just saw. And so I'm going to run this. This one should be fine. Also, I just want to emphasize that, like, the Sudoku problem that I worked on, the input were just integer, but in this case we are given a bunch of strings. So I didn't want to like modify too much in this code, so I took lazy approach to this. So I basically just, you know, given this like board input, I just made everything into the integer, right? And then like this dot, I just changed that to 0, like this dot you see here, like the empty block. And then when you get the Sudoku, so when you use our Sudoku solver, we will modify our board, and then we just change that board, which is just a bunch of numbers, integer, back to the string. So that's the step that I took. I just didn't want to modify all these codes. So let's run this. So this one should be very fast. And if you can go to Apple App Store and then try to download, say, you know, Sudoku app, and you can try like all those really hard problems. Usually hard problems, they are, you know, you are not given many numbers to begin with, and then you can see the difference is like really huge. So anyway, that's for this video, and I will have a link down there to the paper that I found very insightful. So that's for this video, and hope you guys have a great day. If my video helps you guys understanding this problem, please subscribe to my YouTube channel, and I'll have more interesting contents out there for you. I will see you next time. Bye bye.